Hi, everybody. This is Dr. Nigro with the screencast for the notes for part one of our unit on Newton's first and second law. So this is going to follow along with the note sheet that I provided in class. If you don't have a copy, feel free to reach out. All right. So first, in dealing with Newton's first and second laws, we've already talked about weight and mass in class. So mass and acceleration due to gravity are both going to be important as we move forward in this unit. But we're going to leave that concept behind for a little bit and start with Newton's first law. So state Newton's first law in your own words. All right, for me, when I think about Newton's first law, it's basically an object at rest remains at rest, or an object in motion remains in motion, unless acted upon by an outside force. So an object at rest stays at rest, or an object in motion stays in motion unless acted upon by an outside, and sometimes this is called unbalanced, which we're going to see in a few minutes, force. All right, so this is just basically the tendency of any object to remain as is, to not change its position or motion. And so what term do we use to describe that tendency? Well, that's inertia. So inertia. All right. What is needed to change an object's motion or lack of motion? That's going to be our unbalanced or outside force. All right. So let's look at situation one as we investigate Newton's first law. All right. An astronaut kicks a soccer ball in space. So the astronaut holds the soccer ball and they're just floating in space. Let's say they're tethered to a spaceship. And they set the ball down in front of them. What happens to the ball and why? All right. Well, if they were on Earth, we'd be very clear about what happened. It would fall towards the ground. All right. But here, because we're in space, nothing will happen to that ball. It will just sit in place where the astronaut set it. Oops. Why? Well, there are no outside forces in space. So there's no gravity, there's no air resistance, there's no friction, there's just basically nothing. So when you set an object somewhere, if you don't give it a push or a pull, it's just going to sit exactly where you left it. All right, so now the astronaut's going to kick the ball. All right, so what happens to the ball and why? All right, so the ball will move. And that motion will be with constant velocity after an initial acceleration and in a constant direction. All right, so in this situation, by kicking the ball, the astronaut has applied a force. So there's an unbalanced force that initially acts upon the ball. But once the ball's in motion, there's no other forces to affect that motion. So the motion will be constant. All right, so basically it's going to move in that direction forever unless acted upon by some other force. All right, so what provided the unbalanced force here? The astronaut. All right, when will the ball stop moving? Explain. Never. Unless acted upon by another force. So the ball will just keep on going forever and ever and ever. All right, so let's take the same situation, the soccer ball and someone kicking it, but we're going to move from space to the Earth. All right, so Messi kicks a soccer ball, but on Earth. So Messi places the ball in the field in front of him. What happens to the ball? Why? All right. The ball sits sits in place because no additional force was applied. All right, as soon as you set it down, it's just going to remain in place. All right, Messi is then going to kick the soccer ball. What happens to the ball and why? So the ball will move because of the outside force or unbalanced force provided by Messi. All right, so what provided the unbalanced force? Well, that again is Messi. And what is the motion? Oh, sorry, is the motion of the ball the same as that seen in space? Why or why not? The answer here is no. On Earth, we have gravity and air resistance, both of which will influence the motion of the ball. So both act as unbalanced forces. As unbalanced. So eventually, the ball will slow down and then stop. All right, so that's a very different situation than what we see in space, where there are no additional outside forces. So on Earth, we have to remember we always have things like gravity and friction and air resistance. All right? All right, so that's really looking at two different situations with Newton's first law. And a word that keeps coming up throughout this discussion is this word of force. All right, so let's just take a moment and define force. All right, force is a push or pull that causes an object to start, stop, or change direction. All right, now I should say that it causes that change in motion only if unbalanced. We're going to see that if forces are balanced, then you're going to have no motion or unchanging motion. All right, now these forces are vectors, just like our acceleration and velocity, which means that they have magnitude and direction. And those are important quantities to know for each force. All right, the sum of all the forces acting upon a single object is called the net force. And we represent that with a capital F with a little net next to it. All right, the net force acting on an object is going to be broken into either horizontal or vertical. All right, we will not be dealing with angled forces for this unit. We decided to skip that this year. We're going to just have purely horizontal and purely vertical. All right, now these forces that are acting on the object can either be balanced or unbalanced. All right, if they are balanced, then they have the same magnitude. So the value, the numerical value of the force is the same, but they are in opposite directions. So they basically cancel each other out. All right, so I have a picture of a tug of war where we have one side pulling to the left with 300 newtons and the other side pulling to the right with 300 newtons, which means that these forces are the same magnitude but in opposite direction, making them balanced. All right, now if I wanted to calculate F net, I have to determine the sign of each direction. So just in general, I'm going to make left negative, I'm going to make right positive, and if I want to calculate F net, it's going to be the sum of these two forces. So that's going to be negative 300 newtons plus positive 300 newtons, and F net is going to be 0. All right, so whenever you see F net equal to 0, then your forces are balanced. All right, if you have balanced forces acting on an object, all right, that object's position and motion will not change. All right, so balanced forces means no change in position or motion. All right, now what if that's not the case? What if instead we have unbalanced forces? All right, so unbalanced forces are forces with varying magnitude and or direction. So we could have different magnitude, we could have different direction, or both. All right. So here again, I have my tug of war. This time to the left, they're pulling with 400 newtons, and to the right, 300 newtons. So these are unbalanced forces. All right. So to calculate F net, again, I'm going to make left negative, right positive, and F net is the sum of those two forces. So I'm going to have negative 400 newtons plus 300 newtons, which is going to give me a total of negative 100 newtons, which means that the net force is 100 newtons to the left. All right. Now, the unbalanced forces acting on an object will change the object's position or motion. All right. So again, if you have balanced forces where F net is 0, all right, you're going to see no change in whatever the object is doing at that time. If it's in motion, it will remain in motion. If it's at rest, it will remain at rest. If instead your F net does not equal 0, then we have unbalanced forces and we're going to see a change. And that change can be either it goes into motion, or if it's already in motion, maybe it stops, or if it's in motion, maybe it speeds up or slows down. Okay? All right, I'm going to pause this video here, and then I'll come back and we'll talk about different types of forces and then how to draw force diagrams.